Okay, so we're talking principal component analysis. 102B. Okay, so let's. So here I'm going to go do a bunch of math today to show you kind of where we deal with eigenvectors and stuff. Okay. All right, so we're going to project from m dimensions to d dimensions. Okay. Okay, and then so PCA, when we do this, we're going to define a total of d vectors, which we will call W sub d, okay? And each vector is m-dimensional. Okay, so each of these vectors represents kind of the linear combination of the current existing m dimensions. Okay, so each of the d vectors, or I'll just say each of the WD vector represents a linear combination of the original vectors. Okay, and so we'll say that so we'll say x and d is the dth element of the projection. X and d we're going to define as WD transpose y sub n. Okay. And so again, what we're going to use is we're going to use the variance as the way to choose our W. Okay, so we're trying to maximize in the projected space. Okay, so when we look at the data, we're trying to find kind of a combination of the existing dimensions. Okay, so maybe a rotation of the dimensions or some combination of that maximizes the variance in the projected space. Okay, and so and then every of the projected dimensions, the second projected dimension has to be orthogonal to the first projected dimension. Okay, so we'll just say each projected dimension is orthogonal to the other projected dimensions. Okay, so that is to say, so orthogonal meaning that if we take the inner product, okay, between vector I and vector j, wi and wj, this is going to be equal to 0 for all I that is not equal to j. Okay. Yes?
The very top, yeah, right to the left, what does it say? We'll define D?
We'll define D vectors.
No, what's the first thing you wrote? What we'll define?
PCA, principal component analysis. Yeah. Okay, and then, and you know, to make our math and our lives easier, we're going to set the constraint that that the length of each vector is equal to 1. Okay, so another way to express that is Wi, that the inner product between Wi and Wi, this is equal to 1. Okay. Okay, so this kind of sets our coordinate system in d-dimensional space, where each W represents a orthogonal direction in that space, right? In the unit vector. Okay, and then and another thing we're going to do to make our lives easier is that we're going to assume that the original dimensions have a mean of 0. Okay, and we'll do this. Okay, so. The original dimensions have a mean of 0. Okay, so this is to say that y bar, the vector y bar, is 1 over n. And we take our vector y sub n, and if we take the mean of all of these from, okay, that this is going to equal 0, so that that everything has a okay. All right, and this. If the data doesn't look like this, we can do this by centering the data. Okay, so if this is not already reflected in the data, okay, so we can do this by centering the data. That is to say, we find y bar and subtract y bar from every value, right? Okay. All right, and we'll start our principal component analysis by finding the projection onto the first dimension. Okay. So we will. Okay, so okay, and so when we do this, when we're just looking into the first dimension, okay, we're basically going to take our vector w, okay, and then when we multiply it against our y data, this is going to result in a scalar, okay? So when we do this, when we project y onto w, it gives us a scalar value exhibit. Okay, so again, we're basically, we might have 40 dimensions of data, okay, 40 dimensions in our original data, and we're finding some kind of rotation or a projection of this down onto a single dimension. Okay, and because it's a single dimension, it's going to return just a single scalar value on the scale of whatever it is. So you have some congressional representative, okay. Maybe we've collected data on their opinions on 40 different political, topics, and then and we're going to project it down onto just a single value, which is going to kind of put them on this liberal, conservative spectrum of something, right? So it just spits out a single number, and based on this single number, we can kind of recreate to some degree these people's opinions and scores. Okay, and so when we do this, what we want is we want to be able to maximize the variance captured in this projection, right? So okay, and so the variance, sigma squared, is just our usual definition of variance, 1 over n times x sub n minus x bar squared, okay, from n equals 1 to n. Okay. Okay, and then we can make our lives easier by saying by expanding this. Okay, so we're gonna we will use the earlier assumption that our y bar has a mean of 0. So if we look at x bar, which is equal to 1 over n times the sum of this. Remember, x is w transpose y. Okay, so we're going to say and because of this, we can pull out the w transpose, this part becomes 0. So we get W transpose times 0, so we get 0. Okay? So we'll have x bar equal to 0. So now our variance is just sigma squared is equal to 1 over n x minus x bar squared. This becomes 1 over n sum of x, this x of n squared. Okay, and then substituting back in what our projection is, sigma n squared we'll take W transpose y squared. Okay, so sub n. So again, we are projecting our data, our complex data y, onto some direction w, which produces scalar values x. Okay, and we're trying to maximize the variance that we're capturing in that x, which is what we have right here. Okay, and then so we'll expand this. And when we do this, this gets expanded to W transpose y sub n transpose W. Okay, this is when we this is what happens when we expand this. Okay, and so we can kind of pull out the W, right? And we'll have W transpose, right, times, here, actually, so the 1 over n is just a constant, so this actually, we're going to have W transpose 1 over n, and then the YY transpose, sum of yn transpose times W. Okay, and we're just gonna okay, and if we recall, remember, so recall that the average of this was 0, so we can kind of expand this to y bar minus the mean of this times y bar minus the mean of this transpose. Okay, does this look familiar? No? Kinda? So when you have, so this thing when it's a vector, this becomes your variance covariance matrix, right? Your covariance, this is your covariance matrix. The covariance matrix. Okay, and so this just becomes W transpose, and then I'm just going to put in, this is, I don't know, some vector matrix C, okay, where, I don't know how to do this, okay, this is a covariance matrix. All right, so if you recall, this is a covariance matrix. Okay, so we want to maximize find the W that maximizes this, which means that's going to maximize this quantity, right? Okay, so we want to find the W that maximizes this quantity. Okay, and so this can be done using kind of a Lagrangian term, okay? Because so you know we have the with the constraint, okay? We have the constraint that the length of the vector, right? So we want to find the W that maximizes the quantity, but we have the constraint that the length of the vector has to be 1, right? Otherwise, we would just alter the size of W. Okay. So so we have this, and so to maximize with a constraint, we can use Lagrange multipliers, right? Okay, and so we'll say the thing we're trying to maximize is this. Okay, and then we subtract off kind of our Lagrange of our constraint. Okay, and then when we do this, and we take the derivative of this with respect to W, what we end up getting is we get 2CW minus lambda W is equal to 0. Okay, and solving for this, okay, is equal to lambda W, and if we just say lambda is some arbitrary constant, okay, then I can divide both sides by 2, and it would just still lambda, right? So I can divide by 2 and still have some arbitrary scalar value. Lambda. Okay. This part, if it looks familiar, this is kind of like the definition of the eigenvectors of a matrix. Yeah? Okay, so this is the definition of an eigenvector. of a matrix, okay? So I guess I could have just said when we do PCA, we find the eigenvectors of our covariance matrix, okay? But this kind of shows us how we got to this point, okay? So if you recall, in the eigenvectors, you've got some matrix A, okay? And the idea with an eigenvector, so we can just take a kind of just eigenvector review. And say you have some matrix, some square matrix A. Right, and then so the we can say that the eigenvectors of A is basically A times some vector u is equivalent to just some constant times the vector u. Okay, so this is the this thing is called the eigenvalue, and this is called the eigenvector. Right. So you can think of a square matrix. When you multiply it against some point, it transforms that point. Okay, maybe it puts a rotation in space, or it moves it to some other place. Okay, here actually we have the okay, let me just get too much. Okay, let me go to visually explained eigenvectors. Here we go. Okay, eigenvectors and eigenvalues. All right, so what we have here, okay, they only show it here. Okay, so here we have some kind of matrix A. All right, and the idea is with matrix A, when you multiply V, so V is a point in space, or it's a vector. It's a vector in space, right? And it doesn't show this, but it says after you multiply A, the kind of the square matrix, A times V takes the point out here, okay? And then changing the eigenvectors of V. I mean, not eigenvectors of V, but changing what V looks like, or A looks like, okay? Multiplying V times A moves it out here, okay? And so, you can kind of think of what these things do. All right, and so the idea being that if we look at how V has been affected by A, it moves it to another location in the space, okay? And so, our original vector goes from here, and then after we multiply by A, the vector A times V takes us out to here. So we can think of A, the square matrix A, as it's some kind of transformation on the vector V. Okay? With an eigenvector, what we're saying is that when you have A, when you have the square matrix A, then anything along this line is an eigenvector. Okay, so that here is V right here. Okay, and so currently V goes from here to here, and then when I multiply it by A, what happens to it? It moves in the same direction. The resulting vector A times V, it's a new vector. This is in line with V. Okay, so the eigenvector is, and in this case we have u's, right? So if we have some vector here, if this is our vector u here, then what this means is that A times u is just a scalar multiple of this. Okay, so this is going to be A times U. Is that it just ends up somewhere out here. Okay, if you have this kind of alignment, this is an eigenvector. Eigenvector of A. All right. Otherwise, if the transformation is not kind of this scalar thing, but you start off with some vector u like this, and then after you multiply it, it ends up it's not aligned here. A times u ends up out here. This is not an eigenvector. Okay. Okay. So when we're talking about some matrix A, we can think of the matrix A as a way to transform vectors in our space, right? So when we multiply a vector by A, a vector u by A, it kind of transforms the vectors to somewhere else, okay? And if that transformation can also be expressed as just multiplying by a scalar, then that means u is an eigenvector of A, okay? As just scalar multiplication. Then u is an eigenvector of A, okay? And so that's what we're saying. We're saying multiplying by the matrix A times u, if that's equivalent to just multiplying a scalar times u, this is an eigenvector, okay? Because otherwise, generally when you multiply a matrix times a vector, you can't just say it's the same thing as multiplying by a scalar. Okay? And so what we see is that the solution to maximize the amount of variance that we see after we project our high dimensional data onto a single dimension, the way this is done is by finding kind of the eigenvector of this covariance matrix. So the quote solution to finding the projection of our data y onto a vector w that maximizes the variance captured by our projection is to find the eigenvector of our covariance matrix of Y. Okay, and then you know, when you have a bunch of these things, you're gonna end up having a bunch of eigenvectors, okay? And so we find the you find the eigenvector with the highest eigenvalue, okay? So you when you're starting off with m dimensions, okay, you're gonna end up having m eigenvectors, okay? Start with m dimensions. Okay, you'll have an m-dimensional square matrix. Dimensional square matrix for square covariance matrix. Okay, and this will have m eigenvectors. Okay, and so the one with the greatest amount of variance is the one with the largest eigenvalue. Okay, and so this is kind of how we start off with principal component analysis. Is that if I can you know, you might have two-dimensional data, okay? Okay. And so here, if this is my data, right? I'm going to have a covariance matrix, right? So my covariance matrix C here, let's say this is I don't know, what do you think my covariance matrix will look like? Okay, maybe I'll have 1 and 4 down the thing, and then there's going to be high covariance between the two. Huh? Well, yeah. So what does that? Okay, I guess we'll just make it 7. Okay, so we'll go 1, 0.7, 0.7, and 1. Okay, and then basically when you find the eigenvectors of this, and I don't know how to remember how to find eigenvectors by hand off the top of my head. We'll have to. Yeah. You find the eigenvectors of this, and what it's going to give you is it's going to give you basically a new vector here, okay? And this is the vector that captures the greatest amount of variance, okay? So I guess, you know, we might run out of time here, but what is this? Yeah, okay. Okay, well, I don't know. All right, so, all right, we'll do this later. Okay.